Welcome to Rich Planet TV. I'm Richard D. Hall. Earlier this year I interviewed Andrew Johnson to tap into his vast knowledge of the Apollo missions and also the evidence of life on Mars. Now today I've returned to speak to Andrew, who's going to teach us some more information about our solar system and beyond. Welcome, Andrew Johnson.
Thanks for inviting me back, Richard.
Okay, now we covered the Apollo missions and Mars, as I mentioned in previous shows, and our assertion is that we don't believe that NASA have been honest about what's really up there. Now we're going to talk about some more objects within the solar system, specifically comets and asteroids and this kind of thing, because you ask a mainstream scientist what is a comet or asteroid, they'll come out with a standard model or a standard view of it, and
right.
you think that it's not quite as clear cut as some astronomers might think. But before we go into comets, asteroids and other celestial bodies, for example, some people allege planets in our solar system that aren't known about, can you go through just a description of the solar system, starting from the sun, working outwards, just to give people an idea of the sizes? I know it's quite a difficult thing to describe in 5 minutes, but...
Yeah, well, I don't think it's too bad. I mean, one of the things that struck me when I started looking into this area of astronomy and some of the cover-ups, and as you said, the things that we've already discussed, was that I've been interested in astronomy for a long time, and I seem to have know things that other people don't seem to know, which is things like the sizes of the things in the solar system, the relative distances. And I think without that basic knowledge, you're much more prone to being subject to victims of disinformation,
right,
which hopefully we'll get onto later. But so one of the key things that you can think of in helping to get a grasp of the size of the solar system is the distance between the Earth and the Sun. Right, and many people, will have a rough idea of what that is, but others don't, and the rough distance is 90 or 100 million miles. It averages at about 93 million miles. Mm-hmm. So we're going around the sun in a circular orbit, and we average at 93 million miles away from the sun. Now, all of the planets, at different distances from the sun, we have Mercury the closest, Venus is the next closest, often described as kind of a sister planet to the Earth because it's about the same size. Then we go out to the Earth, then to Mars, and then in between Mars and Jupiter we've got the asteroid belt, mm-hmm, and then we've got Jupiter, Saturn, and then we've got Uranus and Neptune and Pluto. So those are the 8 planets in the solar system. They used to class Pluto as a planet.
Just to quickly interject, Andrew, am I right in thinking that all of the planets go around the sun this way, but Venus goes around the opposite way?
That's not quite correct. The planets all orbit the sun in the same way, mm-hmm, but the orbit of the planets rotating on their own axis, their actual day, mm-hmm, Venus has a motion which is called retrograde. In other words, Venus's spin is the opposite to the other planets, right, which is very curious, because if you think of the physics involved, we've both studied physics to some degree, and we have this thing called angular momentum, mm-hmm, and when you fire something which is spinning, or something which is spinning that breaks up, or something that is spinning changes its motion in some way, angular momentum is always conserved. Mm-hmm. So if the theory about how the solar system was formed, where they allege it's formed out of a rotating disk of material, so it should all be rotating the same way. So for one planet to end up spinning the opposite way to all of the others, that's quite unusual. That's not easily explained by the standard.
So it doesn't
model
go around the sun the opposite?
No, it goes round on its axis,
on its axis.
Yeah,
okay,
correct.
So if we say that 93 million miles is one astronomical
that's
unit,
correct. Yes.
How far are we talking about to Pluto, to the last?
I think it's about 40 astronomical units,
right,
around about that sort of figure. It's about 4 billion miles away. Mm-hmm. So in other words, one astronomical unit is roughly 100 million miles. So, you know, 1 billion miles is approximately 10 astronomical units.
Right, and now there are a couple of other planets, or planetoids, do people call them? Because Pluto is not a true planet, is that?
Well, they used to class Pluto as a planet up until, I can't remember when the ruling was made, but it was about 5 or 6 years ago. They decided that Pluto is too small to be called a planet, so they've characterised it either as a planetoid or a dwarf planet.
Right.
And I think, you know, you'll see both those terms used. And Pluto is actually smaller than our moon. They've now got a much better measure of its size, and I think it's about 1,000 miles in diameter, and I think the moon is like 1,400. I can't remember the exact figures off the top of my head, but it's round about those sorts of figures.
Right. So are there any other planetoids other than Pluto?
Again, that's something that seems to have been detected in the last 10 years and more. We've had several named planetoids which mainly have been detected by studies that NASA have done. One is called Sedna. That was talked about in 2003, and I think that's around about 1,000 miles in diameter. And then we have Eris. You know, we can show some graphics of these from the websites and so on. And then we have Makemake is another one, and these are all way out beyond the orbit of Pluto, so they're a long way off. And I think one of them, Eris, is 800 miles across. So these are relatively small objects. You know, they're smaller than Pluto, but they're a long way off.
So how many times further than Pluto away from the Sun?
The Sedna planetoid, or the dwarf planet, it's 3 times further away than Pluto. So it's approximately 12 billion miles from us. It's a long way off. And the diameter is about 1,000 miles.
Right, right. All right, now within the solar system we have other belts or bands, one after Mars and then another one right at the edge of the solar system. Can you tell us about those, Andrew?
Right, so basically we have the asteroid belt, which we you know, can be fairly easily observed. I mean, even if you have, for example, a small telescope, you can't see it as a cloud of debris, but you can, for example, see some of the larger asteroids. There's Ceres and Pallas are 2 of the larger asteroids, which I think if you've got a good telescope and you know where to point it, you can actually see those through a telescope.
Right.
And they're between the orbits of Jupiter and Mars.
And there are thousands of asteroids.
Yeah, there are thousands of asteroids. I don't know how many they've catalogued, but there are, you know, several thousand, I think, that have got names.
Right. And do these asteroids all rotate in the same orientation as the planets?
I'm pretty sure that they do. I don't think they would be orbiting in counter direction, because there would then be too many collisions.
Right. But this zone, it's spread over a huge area between these 2 planets.
Yes, yes.
Right. And does it extend within the orbit of Mars or within the orbit of Jupiter, or is it contained?
It's contained within a relatively narrow band. I don't know what the exact width would be, but you're talking, you know, probably a few thousand miles to maybe a few tens of thousands of miles. I don't think it's much wider than that.
And I would say that the most obvious thing which would spring to my mind would be, well, were those asteroids once a single solid planet? And we'll come on to that.
We'll mention that, and some, you know, the argument has always been, as I've understood it, or is it from the asteroid belt from a planet which broke up, or from one that never formed?
Right.
So, you know, is it some leftover material that started to accrete into a planet and then failed for whatever reason?
Now we have a belt further out as well. Tell us about that.
Yes, these again are sketchy in my knowledge. And one is the so-called Kuiper belt, which again is meant to be something like the asteroid belt, but I think the Kuiper belt is more theorised. They can't directly observe it, I don't think, to my knowledge. It's only they've inferred its existence from the motions of various bodies which they think have come from that region of space.
Right. And
then out beyond that, which is said to be some kind of limit to the solar system, is the Oort cloud. That's OORT, the Oort cloud, proposed by Jan Oort, who I believe was a Danish or a Dutch astronomer, and he suggested that was where the leftover material, which, you know, was around when the solar system formed. We've got this cloud of material which is like a sphere around the disk of our solar system.
Yeah. All right. Now, one term that I've heard used is the history of the solar system, which I think is quite relevant to what we're going to talk about. And one of the things that astronomers look at to try and determine how the solar system formed and what its history was is comets. Just tell us about comets. How common are they? How many are there? How big are they? What are their orbits? How far away are they? Just give us a background on comets.
Yeah, well, this is again the excitement over Comet Ison, which was recently seen in our skies very briefly. There was a lot of excitement about that, and they're claiming, as you say, that if you look at the comets, you can calculate certain things about them, you can observe certain things about them, and that will then teach you about the early solar system, because the basic idea is that comets are from the cloud of material from which the solar system formed.
Right.
Aeons ago, billions or hundreds of millions or billions of years ago.
Yeah.
And so the idea is that if you see a comet coming in, you get your telescope on it, or you do a spectrographic analysis of the tail, and you can see what chemicals are in the comet, and therefore you can see what chemicals are in the early solar system and stuff like that.
So a spectrographic analysis is measuring what frequencies of light are within the comet is giving off, and scientists know based on the frequency what elements are in there. Okay,
That's right.
We'll come on to that. But what about the orbit of comets? Just describe how they're different to planets.
Yeah, well, planets have roughly circular orbits, or very close to circular orbits. Most of the planets do. Some of them are slightly less circular than others, but in the main, they're circular orbits. Comets, however, generally have an elliptical orbit, which is like an oval shape, and they tend to spend most of the time way out in the solar system. But then they come in, when they come into the solar system, they rapidly accelerate, and then they get they come around the sun, and they speed up.
So it will be kind of like this,
like a slingshot. Yeah.
Yeah, and then it's come around like that.
Exactly.
So there's a lot more forces are at play as it's going around the back of the sun and then back out again. So as you say, like a slingshot.
Yeah, you can get the slingshot effect.
Okay.
And the thing that's we'll probably mention once or twice as we go through this is perihelion, which is where the comet is closest to the sun. Perihelion, helion being the sun, and peri, I'm assuming, means closest or close approach.
Right. So there are various popular comets that people will have heard of, such as Hale-Bopp, Halley's Comet, Ison, Elenin. These are names of comets that have come past in the last sort of 20 years.
Right.
But what's the sort of magnitude? I mean, how many comets are there going around the sun in 1 year, say?
There are quite a number. I mean, again, the place to go and look is the Minor Planets Centre. So if you Google that, we'll probably be able to get the website, on the screen here. But if you go and look on there, they keep track of all the comets that have been discovered, and this is a very important sort of concept that people need to get to grips with. In that there are, we've got, obviously, as you said, people have heard of Comet Halley, they've heard of Comet Hale-Bopp, and amateur astronomers, they get a kick out of having a comet named after them. That's their goal, is to get one of these celestial objects named after them. It's quite an incentive, if you can get something that comes around the sun named after you. So they've got thousands of pounds of equipment which they use to try and detect these comets. And so, for example, when I last looked at the Minor Planets website last month, I looked in about the second week of November, and they'd already discovered 3 new comets just in that month.
So what would be the difference between a comet and a near-Earth object then?
Well, a comet would normally, I think, comet doesn't come within the orbit of the moon, for example.
Right.
If an object came within the orbit of the moon in distance, and the moon is only like 200,000 miles from us, again that varies slightly, then that would be classed as a near-Earth object.
Right, okay.
I don't know whether there's a cut-off figure which distinguishes between a comet and a near-Earth object, whether they say if it comes within 1 million miles, then it's a near-Earth object.
An asteroid presumably is one within that particular belt in a circular orbit.
Yeah, allegedly. But again, as I've got a couple of slides where it seems that asteroid can behave like a comet.
Right.
So
and possibly an asteroid can become a comet.
Yeah, potentially.
Right.
Potentially.
All right. Now, there's quite a lot of probes gone near or crashed into and sent data back from various comets over the years.
Right.
So, because there is a bit of argument over what a comet is made of, am I right?
Right. Well, that's one thing we haven't really spoken about yet, and again, it is quite important to talk about that, because this is one of these things where, when you start to look into all of these topics, you realise you're being fed a certain set of statements which you're expected to believe.
Mm-hmm.
And one of those sets of statements is about comets,
Mm-hmm.
because before the 1950s, nobody really was quite sure what comets were, and they didn't really have good ways to see how big they were, because what you see when you see a comet is essentially a cloud of dust, and what's generating that cloud of dust, you don't know the actual size of it. It's a bit like if you were to put a balloon around something and blow up the balloon, you just inflate it with air. You wouldn't know how big whatever was inside the balloon was until you popped the balloon, and then you might see it was as big as a golf ball or a football, or it was as big as a pea. You wouldn't really know how big it was. Comets have this bright glowing material around them, and then they have a nucleus within that bright glowing cloud. The cloud of material is called the coma, and then you have the centre, which is called the nucleus. So what was proposed by Fred Whipple in the 50s is that a comet is basically a dirty snowball.
Mm-hmm.
So in other words, if you imagine you've got this snowball flying around the sun in a highly elliptical orbit, most of the time it's out in the frozen wastes of the solar system, and then every certain period of years, with Halley's comet it's 76 years. With other comets it can be thousands of years depending on the orbit. With other comets it can be as low as 6 years.
Mm-hmm.
It comes in, and as the snowball gets close to the sun, of course the snowball melts, the ice turns into water vapor, and then we have this thing called the solar wind, which is like a stream of particles which comes off the sun, and that crashes into the water vapor that's been boiled off the surface of the comet, and then that creates the stream of material which creates the visible tail. That's the standard theory. In other words, a dirty snowball, it's a snowball with dust stuck into it, and it melts as it's coming close to the sun. That's the standard theory.
I mean, the gut feeling with that is it's not going to last very long.
Right, precisely, particularly with those that go very close to the sun and are subject to intense heating. Right. But some of the comets are bigger than others, though. So some of them, their nucleus, the little core of material, can be as small as a mile across.
Right.
And I think below that size, they probably wouldn't be called comets. They would be called something else.
Right. And
you probably wouldn't get much of a tail. But the comet Hale-Bopp was around about 15 miles across on the nucleus.
All right, and we'll just hold it there. We're going to talk more about comets and some of the probes that have investigated these comets, and also the electric theory of comets after this. Welcome back. I'm talking to Andrew Johnson about comets. Now, you explained the standard model or the standard theory of comets, that they're dirty snowballs. Now, there's a great deal of contention over this, Andrew. Just to explain why.
Well, I don't think actually there's not that much contention in the mainstream scientific thinking. You get a few people who will say, well, these things can't be correct, but again, I was looking when I was doing research for this latest presentation that I was asked to give because of Comet Ison coming into the solar system. I went onto the GCSE Bite Size, the BBC revision website, and it says, comets are dirty snowballs. Get all
of your best research.
Yeah, of course.
You just go straight there. That's
yeah,
all you
that's
need to
right.
know,
Yeah, BBC websites where everything that you need to know is, as we both well know. But that just said comets are dirty snowballs. End of story. That's all you need to. That's all the kids need to know. End of. But again, if you start to explore the actual data that's come back from the probes, and that's been one of the killers for me. Mm-hmm. I was familiar with some of this data. For example, you mentioned a few minutes ago about how we've had, I think we've had three probes that have gone gone very close range to comets. One brought back cometary material with a sample and return mission. Another one fired a probe into the head of the comet. And another one flew. It was actually the Giotto probe, as long ago as 1986, which flew towards Halley's Comet, and it counted the impact of material before the camera was destroyed by the material being given off by the comet. And they didn't really know at that point what the nucleus was going to be like, and they set the camera to go to the brightest point of the comet. But as they found, the actual surface of the comet was sort of like a dark coloured tarry material, like a bitumen material,
right.
which was a bit of a surprise, because that's not the colour of snowballs. I mean, unless it's a very, very dirty snowball, you'd expect it to be a lighter colour with ice.
So am I right in thinking that one of these probes found that there was way less than 10% water?
Absolutely, and this is one of the things they've tried to sort of couch in different terms. Again, if you look at the, in fact, I've got a good quote here. We'll go forwards to that quote.
All right.
Now, on April the 5th, 2002, we had a NASA spacecraft. It flew past Comet Borrelly, and Comet Borrelly, again, was said to have been described as a dirty snowball. But the headline on the NASA's website says, Comet has hot, dry surface. It has a hot, dry surface. And that's what they found. And it says, Dr. Lawrence Soderblom of the US Geological Survey's Flagstaff, Arizona station, lead author of a report on the Borrelly flyby results appearing in the online edition of the journal Science, said, "We know the ice is there," he said. "It's just well hidden."
Okay.
So what he's basically saying is, we've got data back from the experiment which shows that we didn't see any water, but we're just going to ignore that because we know that we know that it's ice anyway.
Right. So
that was in 2002, and that was before the Stardust mission. Now the Stardust mission is even more interesting because they sent this Deep Space One probe. This Stardust mission, they sent it to Comet Wild 2, Comet Wild 2 I should say, because it's named after a German guy, and that was in 2004. And that when that got there, the probe was designed such that it collected material which was being ejected by the comet as it was coming close to the sun, and it collected that material in what's called aerogel, which is kind of like a sort of like blue tack, I suppose. And the stuff, the particles flying off the comet stuck into that, and then they brought that material back in a capsule, and it landed in the desert, and they retrieved that under clean room conditions and everything, and they were able to take that material away and actually do mass spectrometry on it to find out what it was made of. And as is pointed out by the Electric Universe video, which I got a lot of this information from, but it's also on NASA's website. You can go and look at this on NASA's website too. What the particularly interesting thing that they found with the Stardust mission was a material called olivine. Olivine. Now that's a mineral which is normally found during volcanic eruption. It comes out of volcanoes, right, or it's formed during the process of either a volcano cooling, the lava cooling, or the volcano erupting then cooling, or within the eruption itself. I don't know exactly when it's formed, but olivine is a mineral, and the thing about it is that if you put it into water, in the presence of water, it will degrade. It will change into something else. It cannot form in the presence of water, right? So they found olivine as one part of the material, but then they found other materials which can only form in liquid water, right? They can't form within ice. They can only form in liquid water. And they actually said, after looking at the Stardust samples that they got back, that the materials that we found are characteristic of planets in the habitable zone of the solar system. Right. In other words, not from the outer solar system.
Yeah, because if we just consider a star or the sun for a moment, if you go a long way away, it's extremely cold,
right,
and certain chemical things can't happen.
All the chemistry slows down with a lower temperature.
So, all right then. Well, let's just distinguish between elements and compounds.
Yes.
We have the 92 chemical elements that everything's made of.
Correct.
Where are they made first, Andrew?
Well, we're told that the up to the elements iron, if you go up in the atomic numbers from 1 up to iron, I can't remember what the atomic number for iron is, but all of those elements are formed during the process of nuclear fusion inside the core of a star.
Right.
So we're told that a star is a nuclear fusion reactor, and all the elements up to iron are formed then. But when you go above iron, they have to be formed by different processes because they can't be formed in a nuclear fusion reactor, and we're told that those elements are formed in supernovae explosions when you have much greater forces of the star exploding, and these elements are then formed during the explosion.
So you have certain elements, and then as they come to within certain temperature regions, you call it the Goldilocks region, certain molecules can then be formed.
Right. Well, that's true. But we're getting then away. We're now into the situation where the star is stable.
Right.
We've got an ongoing reaction of, for example, fusing hydrogen into helium, which is allegedly what's going on in the sun right now, and it gives us all our energy. That's what we're told. And that process then creates heat and light and radiation. And around a star, you have planets which can then soak up that heat. There are other chemicals on those planets which then start reacting with each other and form these various compounds, like they form water, for example, from hydrogen and oxygen, and they would form methane, for example, from carbon and hydrogen, and they would form things like carbon monoxide and carbon dioxide. So those are all formed as a result of chemical reactions rather than nuclear reactions.
All right, so tell us what the standard model for comets is, and why the accepted theory suggests that there shouldn't be certain elements and molecules on a comet.
Right, so the standard model is basically that a comet is some bits of dust stuck into a ball of ice.